Hey everyone, you've probably noticed it, right? You ask an AI chatbot a question, and it starts typing back, almost like a person, but word by word. Well, today we're going to pull back the curtain and look at the amazing engineering that's making these models faster and more efficient every single day.
You know that feeling? Waiting for the AI to finish its thought? That slow, deliberate generation of text isn't just for show. Nope, it's actually a clue pointing to a massive challenge deep inside the AI's architecture. To understand why it's slow, and more importantly, how a bunch of clever engineers are making it faster, we've got to look under the hood.
So our journey starts with something called the transformer. It's the engine behind basically all the big models you've heard of, like GPT and Llama. And at the very heart of the transformer is this brilliant, beautiful mechanism called attention. It's how the model figures out which words matter most and how they all relate to each other.
And you know, this quote from way back in 1787 absolutely nails it. For an AI to remember what you just said and give you a response that makes sense, it needs to have a really powerful way to pay attention. And the original transformer architecture, it took this idea and put it on steroids. See, the creators didn't settle for just one attention mechanism. That would be too simple. Instead, they used a whole bunch of them, all running in parallel. On the left here, you see the basic concept. But on the right, that's the big upgrade, multi-head attention. Think of it like giving the AI dozens of eyes, all looking at your text from a slightly different angle, all at the same time.
So yeah, the official definition is that multi-head attention, or MHA, lets the model process information from all these different perspectives at once. And this is fantastic for understanding really complex stuff, like grammar and nuance. But to really get a feel for how it works and why it creates a problem, let's use an analogy.
Imagine a giant library. Your prompt to the AI is a research topic. The AI sends out a whole team of researchers. These are what we call the query heads. Now, in a standard MHA setup, every single one of those researchers goes and checks out their own personal complete set of reference books. It's super thorough, right? But you can just imagine the chaos and the traffic jam at the checkout desk.
And that traffic jam, well, that brings us right to the heart of the problem, the inference bottleneck. Because there's this massive difference between how an AI model learns and how it actually talks to you.
When the model is training, it's like it gets to read a whole book or the entire internet all at once. It's super efficient, but when it's generating a response for you, that's called inference, and it's a totally different ballgame. It generates one word, then it stops, reads the entire conversation, including that new word, and then, and only then, does it generate the next word. It's this step-by-step process that grinds things to a halt.
And here's the real kicker. The problem isn't the raw number crunching. The true culprit is something called memory bandwidth. For every single word it generates, the model has to go back and reload those giant sets of library books. The technical term is key and value tensors, from the GPU's slow main memory into its super-fast cache. It's this constant fetching of data that eats up all the time.
And we can actually put a number on this. A really important paper from 2019 measured this exact cost. For a standard MHA model, it took about 46 microseconds for every single token it generated. Now that might sound incredibly fast, but in the world of computer chips, trust me, that is an absolute eternity. And it adds up fast. So this Maori problem was such a big deal that it kicked off a whole new wave of research. People started asking, how can we reduce that traffic jam at the library checkout? What if the researchers could just share the books?
And that thinking led to the invention of multi-query attention, or MQA. And the idea behind it is just brilliantly simple. You still have your big team of specialist researchers, those are the query heads, but instead of each one having their own massive set of books, they all share one single common set of keys and values. This diagram just shows the change perfectly. You can see it on the right. With MQA, all of those blue query heads are all pointing to the same red key and yellow value head. This just massively cuts down on the amount of data that has to be shuffled around from memory at every single step.
So what were the results? Well, they were absolutely staggering. That same paper that clocked MHA at 46 microseconds found that MQA got the job done in just 3.8 microseconds per token. That's more than a 10 times speed up. I mean, that is a total game changer.
But you know how it is in engineering. There's almost always a trade-off. When you push one thing to the absolute extreme, sometimes you have to make a little compromise somewhere else. The hunt for the perfect balance was officially on. So you gotta ask, is raw speed the only thing that matters? Well, researchers found that MQA, while blazingly fast, could sometimes cause a small drop in the model's overall quality, and sometimes it even made the model a little bit unstable during training. It turns out that sharing everything was maybe a little too aggressive.
And this is what led to the next really brilliant idea: grouped query attention, or GQA. And it is such an elegant compromise. Instead of every head for itself, or all of them sharing just one set of keys, you divide the query heads into a few smaller groups, and then each group gets to share its own set of keys and values.
Let's go back to our library one last time. MHA was every researcher for themselves. MQA was one giant chaotic communal table. GQA is like forming small, specialized project teams. So the history researchers get to share one cart of books, the science researchers get to share another. It's way more efficient than MHA, but it's much more organized and robust than MQA.
And looking back at our diagram, you can literally see GQA sitting there, right in the middle. It keeps multiple key and value heads, which gives it more expressive power than MQA, but way fewer than the original MHA, which is what keeps it so fast and memory efficient.
And the data? The data proves it works, big time. This chart shows a huge model tested with all three methods. You can see MQA is a little bit lower in quality than the original MHA. But then look at GQA. Its quality score is 47.1, which is practically identical to the original's 47.2, all while being nearly as fast as MQA. It really is the best of both worlds.
So after this whole journey from a complex problem to a series of really clever solutions, what's the big picture here? What does all this actually mean for the future of AI?
Well, it tells a really clear story of innovation. We started with MHA, which was powerful but incredibly slow. Then came MQA, this radical simplification that gave us incredible speed, but it came with a small cost to quality. And finally, we landed on GQA, this refined, balanced solution that now powers so many of the state-of-the-art models we're using every single day.
And this whole saga is really part of a much bigger trend in AI research. As this quote from the creators of another famous optimization, Flash Attention, points out, the cutting edge of AI isn't just about dreaming up smarter algorithms in a vacuum anymore. It's about being I/O aware, designing things that respect the physical, real-world limits of the hardware they run on. Which leaves us with one last big question. This incredible chain of innovation has pretty much solved the attention memory bottleneck, giving us much faster AI. But the race for speed is never over. So the question is, what's the next big bottleneck we need to break through in our quest for a truly instantaneous AI?